This is part 3 in a series of videos about stardust. In this episode, we're going to be talking about how stars pulsate and pulse and what that means for their mass loss. So last time, we talked a little bit about how low mass stars, there's actually stars from about 1 to 8 solar masses, pulsate and how this manifests itself in terms of dust. So here you can see a star that is pulsating, and so the surface is moving in and out. And so what we have is that for these low mass stars, and again it's usually lower than about 8 solar masses, we don't get carbon fusion in the core, but we get this pulsation, and this pulsation gives rise to material being pushed away. So we've got these low mass stars and they're pushing material away, and at some distance from the star, that material that is all atoms and then molecules will form dust. And so for a low mass star like the sun, during its main sequence evolution, it's going to have a solar wind or stellar wind that is very much weaker than what happens later in its life. So the solar wind is typically about 10 to the minus 14 to 10 to the minus 20 solar masses per year. It's tiny. It's about equivalent to how much mass it loses by converting hydrogen to helium and making energy out of the missing mass. Now, if we have these aging stars, so a star like the sun, as it dies, it starts to lose mass much more strongly. That is, basically, there is the pulsation, and the pulsation is driving the mass loss. And it can be anywhere from about 10 to the minus 8 to about 10 to the minus 5 solar masses per year. But more typically around a millionth of a solar mass per year. At the same time, the expansion velocity, that is the velocity at which this material is moving away from the star, is only about 10 to 20 kilometers per second, which sounds fast, but our solar wind right now is moving at 200 to 1,000 kilometers per second. So you've got all this material that is moving away from the star, and it's not moving very fast, so the density of material is quite high in that region around the star. And so at some distance from the star, you start to form dust. And in this picture of the Egg Nebula, what you're seeing is shells of dust that are around the star. The star is hidden behind this dust lane here, and it is then reflecting light towards us, but we're seeing that material that's been thrown out over time. And this is a little bit like tree rings. So here you can see a kind of animated version of this. I've got a star that pulsates, and the star is down here. This is in astronomical units. So the star is actually going to be of the order of about an astronomical unit in size. And so it's getting bigger and smaller. And when it gets to its biggest, some material is going to escape because it's moving in that direction, and it's going to keep moving out. And then it's going to form some dust. Now, the density, and here the color scale reflects the density is always going to be highest near to the star. As it's going out into space, it's spreading out into bigger and bigger volumes. So the density goes down, but you can clearly see that you would expect these periodic enhancements in the density as you move away from the star, as material is flowing away. So let's just revisit the asymptotic giant branch again. Remember, this is what happens to a low mass star as it dies. It becomes a red giant, and then it becomes smaller again. Then it becomes an asymptotic giant branch star, or AGB star. This is the second red giant phase. And so we can see here that during the asymptotic giant branch, the star is getting cooler and also brighter. That means it's getting bigger and bigger. And so over time, you've got the star that is getting bigger and bigger. And so the surface gravity is getting lower and lower. Remember that gravity goes as 1 over r squared. So at the edges, you're going to have very low surface gravity, and that surface gravity is going down all the time as the star gets bigger and bigger. So it's easier for it to lose mass. So there is an expectation that these stars, as these outer envelopes are pulsating, they're going to lose material, but that pulsation is going to change over time, possibly get longer period, but also bigger. And also it's going to just get bigger in general. And so we should have more mass loss over the course of this phase of evolution. So we start with something that's losing a little bit of mass every year, and it's going to lose a little bit more as time goes on. And so over the 100,000 or a million years that it takes for a star to go from the beginning to the end of the asymptotic giant branch, it's going to get increasingly higher mass loss rates. And so what we get then is an evolution of the shells of dust around it. So you can imagine a situation where early on, at the beginning of the AGB, you've got a star. Here's my star. They're not really that shape. And as the material flows away at some distance, it's cool enough to form dust. So I've got dust forming here, and it's drifting away. So early on, you've got something that the gas is low density, so the dust is low density, and it's also optically thin. What that means is you can see through it. And you can see here, we can still see some of the background stars through it. It is also geometrically thin. That is to say, it hasn't been that long that it's been making dust. So the dust that's furthest away is not that far away. And so the shell is not very thick in terms of this distance here, but it's also not that dense. And remember, the optical depth depends on the opacity of the dust grains, the density with which they are packed, and the path length. And since the path length is small and the density is low, it is optically thin. But over time, the star is going to get bigger and bigger, and so we're going to get more and more mass loss. It's also going to be doing it for a long time. So towards the end of the AGB, we're going to have more material being lost. Now you'll notice that I made the inner radius smaller. And this is because actually as the density goes up, the pressure in the gas phase goes up, and so you can actually form your dust closer into the star. So you're going to have an evolution in size both sides of the dust shell. So at the inside, you're going to have it closer to the star because the density is high enough, the pressure is high enough, you can form dust at higher temperature. Also, your star is getting cooler, so you can move it in a little bit. But it's also been losing mass for a really long time, and so the size of the dust shell is very big. And so here we have something that is geometrically thick, that is the distance from the inner edge to the outer edge is big, but it's also going to have more dust in it because the star is losing more mass every year. So that increase in pressure is giving rise to more dust formation. And so you've got more dust, higher density, and a longer path length. So it is also definitely optically thick. That is, you can't see through it. And you'll notice for this one, maybe at the edges, we can just see through the shell, but for most of it, we cannot see through the shell to the stars behind it. But at the end of the AGB phase, that is when there is no longer enough pressure in the envelope of the star to support it against gravity, that outer envelope of the star starts to collapse. That's the end of the AGB. It no longer loses mass. It's not pulsating. And what we get is the post-AGB phase. So in this case, this dust that was formed here, it's just going to keep going outwards. Remember, it's being pushed on by radiation pressure, so it's going to be pushed out in this direction. So we get a bigger radius. The star is also getting smaller and hotter. So you can see I've presented my star as being smaller and hotter. And so this dust is much cooler because even though the star is hotter, it's moving away, and so it's not being irradiated as much. And the brightness stays the same even though it gets hotter. And so you can see in this case, the dust is now spreading out. It's this dust shell, but it's now spread out to a larger radius. So the path length is probably about the same, but it's now more spread out. And so even though its geometrical thickness is about the same as the late AGB, the optical thickness, the optical depth is now less because the density is dropping. And so now you start to see the stars back through it. And so these are all places that we can look. We can look at stars in the early AGB, all the way to the late AGB, and then beyond in the post-AGB phase as this system is heading towards becoming a planetary nebula. Now, there's a couple of different things that we can look at when we're looking at these sorts of stars. One is the morphology. What I mean by that is both small and large scale structures of the shape of the dust shell. The other thing we can look at is the mineralogy. And by that, I mean the composition and crystal structure and grain size of the material that's forming in the dust shell. So we have both the shape of the dust shell and what it's made of. And those are two different studies that we can do, and they will be interrelated. When we're thinking about that shaping effect, here what I've got is, this is looking at the idea of hydrodynamics. That is to say that you're going to have turbulence in your dust shell. This is a model of an AGB star's dust shell. We've got gas that is flowing away from the star, and at some distance, it's going to be cool enough to start forming dust. In this case, it's assuming it's all carbon, and that it's going to make amorphous carbon. But because you've got different speeds of atoms, that are coming off at the same time. Remember that at any given temperature, you have a distribution of speeds. And so as the material is flowing away from the star, it has all different speeds. And so you're going to have some interesting interactions. And what you get is turbulence that gives rise to different densities. So this is basically showing you the density. This is actually the log of density. So this is 10 to the minus 10, 10 to the minus 12, 10 to the minus 14 grams per centimeter cubed. And this is just space around the star. And you can see that you've got some places that are higher in density and some places that are lower in density. And it's not just a nice simple trend from high density close in to low density further out. But this has an interesting effect because nucleation of dust grains, that is the formation of the dust grains, is going to be strongly dependent on the density of the gas. And so what you can see is this then translates to a fractional condensation. So you've got how much condensation happens really depends on how dense it is. So in very dense regions that are cool, you're going to get lots of dust forming, whereas in low density regions where it's still hot, you have a lot less dust forming. And so we can see that you might expect to see some interesting small scale structures where the dust forms, as well as seeing an overall trend as you move away. We'll talk about some of the other shaping effects in a future video. One of the other things that I want to talk about briefly is that as well as pulsating, the AGB star has what's called thermal pulses. So these are two different things. The regular pulsation that happens, and the time scale is of the order of a couple of months to a couple of years. That is due to being unable to maintain hydrostatic equilibrium because of the phase change of helium in the mantle. So we've got this non-burning envelope, there's lots of hydrogen and helium, and the helium can never reach equilibrium. We talked about that in the last video. But there's also another thing that happens because of the helium burning shell. In the helium burning shell, what we get is something that, whether or not it is actually burning, that is fusing helium to make carbon, is very temperature sensitive. And so what you get is something where when it's hot enough to switch on, it will switch on helium burning, but then it's making a lot of energy and it will heat up and expand. Helium switches on and the shell expands, but in expanding, it's using energy and it cools down, and it can drop below the temperature needed to fuse helium. And so at that point, the helium fusion switches off, but now it doesn't have as much energy. And so gravity wins and the shell will contract. Helium burning switches off and the shell contracts. But in contracting, it's converting potential energy to kinetic energy, so it's heating up again. So it's going to get hot enough to switch on the helium fusion again. And so the helium ignites again and we start over. So basically, we've got helium switches on, the shell expands, helium fusion switches off, the shell contracts, helium fusion switches on, and we're back up to here. This happens on a time scale of the order of 10 to the 4 or 10 to the 5 years. So this is a much longer scale thing, but it also has a bigger impact on the internal structure. Whereas the pulsation that happens here due to helium getting more or less ionized, that is not going to have a huge effect on the overall structure. It's causing the star to get bigger and smaller, but it's not going to have a huge effect. Whereas when the helium burning switches on and off, it's going to have a huge effect. One of the things is that the hydrogen burning shell here, that's not always switched on either. And it's likely that they will be switched on at different times. So as this thing expands, it's going to affect the hydrogen burning shell. And so it's going to affect how bright the star is there, but it's also going to affect the overall structure. And this is just kind of the same idea. Now, this view graph was for the sun, solar thermostat, but this is kind of what's going on here. You've got something where a slight drop in temperature is going to decrease the amount of fusion, and so the temperature drops, and so that causes the pressure to drop, and that causes the core to contract, and so it heats up, and so it switches on again. Likewise, when the temperature goes up, the fusion rate goes up, the core gets larger, but in getting larger, it uses some energy, it cools down, and so it contracts again. And so you just have this cycle. That's what's happening in this shell of helium, but it's actually, instead of just regulating the rate of fusion, it's switching the fusion on and off. Getting back to this idea of how the helium switches on and off, it affects the luminosity. And instead of affecting the luminosity in terms of just the pulsation that we see over the course of a couple of years, what we get is something that is changing from a luminosity of less than 2,000 solar luminosities all the way up to nearly 10,000. And you can see here the time scales. This would be for a 1 solar mass star. And so you can see the time between each of these pulses is actually of the order of 100,000 years. And it's going down, and that has to do with how the star is changing over time. Remember, the star is losing mass, and so the amount of material that's supporting is going down. And so that's one of the reasons that this changes over time. So what we've got is, over the course of 1 million years or so, you're going to have maybe 3 or 4 thermal pulses, and that is going to have an effect on what's happening inside the star. So let's go back to the inside of the star. We saw this before, and we were concentrating on how it's pulsating at the surface. But now I want you to look at what's going on down here. We have convection currents that are bringing material up to the surface. So we have something that we've got helium fusion going on down here, and it's making carbon. And that is actually changing the structure inside the star. And then we get convection currents that actually bring the material all the way up to the surface. So you can think of it as being, we've got the pulsations and the thermal pulses. They actually give rise to a change in the structure, and that changes the opacity in this area here. And that gives rise to convection. Whether energy is traveling from the core or near the core out to the surface as radiation or convection depends on the opacity in here. I'm not going to go into that in more depth than that, but basically what's going to happen is, once the convection switch is on, you're going to have material that starts off down here, and it gets pulled all the way up to the surface. And so what we get is new material being formed down here, and it's being pulled all the way up to the surface so that we see it here. And then when the star pulsates and material escapes, it contains some of that new material. So here I have my AGB star. It's not that color. It has this carbon core that is not really doing anything. It's just sat there. Around it, it has the helium burning or helium fusion shell, and that is doing this triple alpha process. We call it the triple alpha process because a helium-4 nucleus is the same as an alpha particle in radiation. So we're taking 3 of these alpha particles, sticking them together and making carbon and releasing some energy. And so here is that same reaction. 3 heliums give me 1 carbon-12. But we also have a hydrogen burning shell. And again, these are not always on, they'll be on alternately. And we'll come back to the issue of hydrogen burning and what it's doing right here. But we also have that helium burning is now making carbon, and then you have convection currents, and the convection is bringing the carbon up to the surface. And so the newly formed carbon down here is actually getting all the way up here. Material formed in this region of the star is now expelled at the surface and pushed out by pulsation. Okay, so what? Well, it turns out that there is a molecule that is very important in controlling the chemistry. The surface of AGB stars is only about 3,000 Kelvin. And at that temperature, carbon monoxide forms very easily. It'll be in the atmosphere of the star, and it's very stable. There are no UV photons to break the bond. So here I've got a carbon monoxide molecule, and this bond is pretty strong. And without any ultraviolet photons, it's going to stay there. But what that means is it's going to affect the chemistry. So stars are generally born with a carbon to oxygen ratio of about 0.4. That is the cosmic ratio of carbon to oxygen. And that has to do with how much oxygen versus carbon gets made in high mass stars and what's been thrown out over time. But for these stars, the AGB stars, as they are making more carbon and dredging it up to the surface, they are going from a 0.4 carbon to oxygen ratio to a higher carbon to oxygen ratio at the surface. That material is now being enriched in carbon. If the carbon is less than the oxygen, then all of the carbon is going to be trapped in CO. You're going to form lots of CO, and then you're going to have only oxygen left over to make dust and other molecules. But once you've made enough carbon and brought it up to the surface that your carbon to oxygen ratio is greater than 1, now all the oxygen gets trapped in carbon monoxide, and you only have carbon left over. And so the carbon is going to dominate the chemistry. And so for these stars, we have basically either carbon-rich or oxygen-rich chemistry. There are some cases that seem to have mixed chemistry, but it's very rare. And in general, they will be delineated as either carbon-rich or oxygen-rich. And we'll see oxygen-rich molecules and oxygen-rich dust around the O-rich stars, and carbon-rich molecules and carbon-rich dust around the carbon-rich stars. So just to show you what a carbon-rich star looks like, here I've got a carbon-rich AGB star. It's pulsating and throwing gas off. The gas is flowing away from the star, and at some distance, dust can form. And this distance depends on what the dust is, but basically a distance where the dust is stable. And the different types of dust that generally form are going to be diamond, amorphous carbon, graphite. So basically different forms of carbon. You're also going to form some polycyclic aromatic hydrocarbons. Silicon carbide is really important, and we'll spend some time on that in another video, as well as some other carbides, and I'll talk about those in a moment, and some nitrides. So here we've got molybdenum, ruthenium, zirconium, and titanium carbide, aluminium or aluminum nitride, titanium nitride. And then we've also got some sulfides. So we've got magnesium sulfide, iron sulfide, iron metal should form, and then this iron silicon alloy should form too. So these are the things that can form. The oxygen is nowhere around, so you make these very reduced compounds. Now let's look at an oxygen-rich star. So here's my oxygen-rich star, and here's the material flowing away, and at some distance it's going to have stability of dust formation. And then we form silicates. Now, I talked about silicates in a previous video, and so you should take a look at those. It's a separate series. Silicates are basically made up of these tetrahedra, where there's a silicon in the middle and an oxygen at each corner. And so these things here that are called olivines, they are made up of these tetrahedra with either magnesium or iron 2+ cations balancing. But you can also have pyroxenes. These are other silicates where you've got chains of these tetrahedra stuck together. And now you have less cations to do the charge balancing, but still magnesium and iron. There are other silicates that may form. Silica is an extreme case of sticking the tetrahedra together, where they're sharing every single apex of the pyramid of silica. But you're also going to form some oxides. So here I have alumina, which is Al2O3, aluminum or aluminium oxide. Here we have spinel, MgAl2O4, hibonite, Al12O19, and then there are going to be some other oxides as well, probably NGO, FeO, that sort of thing. Okay, so these are the things that we expect to form. Now, the last thing I want to talk about in this video before we get into looking at individual dust shells is some information we get from meteorites. So there are these things called presolar grains. They are found in a type of meteorite that are called primitive carbonaceous chondrites. So these are things where basically during the formation of the solar system, the material agglomerated, but it never got hot enough to melt. And so the material is largely in the same form it was in the early solar nebula. And some of it is in the same form it was before it entered the solar system. So it's the material that existed before the solar system, was there when the solar system formed, and has just got stuck inside of this agglomeration of dust and bits of rock. For the presolar grains, they have isotopes that suggest formation outside the solar system. Just to be clear, items that form in the solar system, they do have slightly different isotopic compositions depending on where they're from, but the differences are very small. They're at the per mil level, so a fraction of a percent. Whereas these are things that have hugely different compositions in terms of isotopes. To give you an example, for the solar system, the carbon-12 to carbon-13 ratio is about 90. And there are some of these grains that have carbon-12 to carbon-13 ratios of just 4. So those are places where there's a lot of carbon-13 compared to what we would expect. And it can go the other way as well and be extremely enriched in carbon-12. Those isotopes not only allow us to determine that they formed outside the solar nebula, but we can compare the isotopic compositions to where we expect the dust to form, what sort of nuclear processes are going on. And there is a previous video sequence on that, that will allow us to identify where the individual dust grains came from. So the first grains to be found were all carbon rich, but that has to do with how easy they are to spot. For instance, silicon carbide is not naturally occurring on Earth except in impact craters. We use silicon carbide in a lot of things. It's a semiconductor, it's a fake gemstone called moissanite. It's in lots of things, but it doesn't form naturally. Whereas out in space, we can find it and we see it by remote sensing, but it's also found in the carbonaceous chondrites, and its isotopes show that it comes largely from AGB stars. We also find diamonds and graphite, and a lot of the graphite also comes from the AGB stars, and we'll come back to those later. Now, later, when we found ways to extract less obviously different grains, we managed to find things like corundum, so that's Al2O3, spinel, hibonite, and rutile. So just to be clear, I called it corundum, but it's also the same composition as sapphires, rubies. Actually, not all of them are corundum. Some of them are amorphous, and since they don't have a crystal structure, they wouldn't be corundum, which is a specific crystal structure of Al2O3. Likewise with spinel, some of them are crystalline, some of them are not. Most of these have been well studied. In more recent times, we've also discovered silicates, but because the silicate grains are chemically identical to solar system and earthbound silicates, they're much harder to see. And we'll come back to those in a future discussion. But we have now found presolar silicate grains in meteorites. So we've got all of these things that we can look at, and we can say, oh yeah, the silicon carbide nearly all comes from carbon-rich AGB stars. And so that gives us some constraints on what we're looking at from the carbon-rich AGB stars, similarly with graphite. And that's where we're going to end this video.